Hello everyone, this is our fifth lecture for the course ENSC107, and in this video we'll be discussing the topic on buoyancy. Now first let's define what is buoyancy. It is a phenomenon where a body either fully or partially submerged, partially a body fully or partially submerged experiences a hydrostatic force or um, a hydrostatic lift due to the increase in pressure with depth. Okay, so if we try to illustrate this scenario, for example, let's say we have a free surface, and we we put a solid body, in this static fluid. So if we put a solid body, this body can either floats or it can also sink. So that depends upon whether the force that's acting upward, this hydrostatic lift or the hydrostatic force, in which we refer to this as the buoyant force. Okay, so if if this buoyant force is less than the weight of the object, then of course this object will sink. But if this buoyant force is greater than the weight of this object, then uh, this object will float. Okay, so if we draw a free body diagram, and let's say we have this, let's say at the centroid where our weight is acting, and let's say this is our weight. It says that in this phenomenon that we have a hydrostatic lift or a buoyant force that's acting as well. Okay, but the direction of this buoyant force is along the upward direction. So let's say this is F sub B. Now, according to the Archimedes Archimedes principle of buoyancy, it says that a body in a fluid, so that's either floating or submerged, is buoyed up equal to the weight of the fluid displaced. Okay, and it says here that the buoyant force okay, the buoyant force acts vertically upward through the centroid of the displaced volume. Okay, so let's try to express this in terms of figures. Now, for example, we have this body and we have this shape. Okay, and then it is on the water or the fluid, for example. Okay, and let's say this is our free surface. This is the level of the free surface. And for now, we are looking at a three-dimensional drawing, and this is our XYZ. And if we try to draw this in terms of the XY plane, what we get is something like this. Okay, so this is our free surface, and then this is our solid body. Okay, so it says in the Archimedes principle that the buoyant force is equal. I mean, the value or the magnitude of this buoyant force is equal to the weight. Okay, so it is equal to the weight of the fluid that's displaced. Okay, so of course um, when you put a solid in a space or in a region of fluid, then that solid will actually occupy some volumes, right? So let's say this is our solid, and if we put it in the water, then instead that this volume is being occupied by the water, it is now occupied by the solid volume, and therefore this volume, this is called the displaced volume of the fluid. Okay, so in this three-dimensional view, this is our displaced volume. Okay, so since it is a volume, then of course uh, there must be some centroid as well. Okay, so this weight, all right, so let's say this, so here's our centroid of the displaced volume, and that's where the buoyant force is acting. Okay, so FB. But the value of FB is just simply the weight of this displaced volume, which is just equal to the unit weight of the fluid times the displaced volume. Okay, so that's the main equation for this phenomenon. Okay, that the a buoyant force is equal to the weight density of the fluid multiplied to the displaced volume. So if our body is just floating, then of course you have to only consider this volume. But if your solid body is fully submerged, then of course that the volume, the displaced volume, corresponds to the volume of the solid. Okay, so let's try to look at this in another perspective. Now, if we have a container right here, and we fill this container with water up to a level wherein it will uh, something like a weir. Okay, so in 3D, if I'm going to draw this in 3D, okay, so if this is our XY, then this will be our X, Y, and this will be our Z. Okay, so let's say it is filled with water up to this level, right? So this is our free surface, and this is our, let's say this is our free surface up to this level. Now, if I try to drop a solid right here or inside this container, then of course the level of the water, this free surface level will rise, and because of this opening, then of course some of the water will be displaced. Okay, so if we try to measure this amount of displaced water, right? So if we try to measure this the amount of the displaced water, we'll be able to find out that that displaced volume is just equally uh, the same. Okay, so displaced volume. And the weight of this displaced volume, right? So since it has a volume plus it has a unit weight, then we can actually determine the weight of this displaced volume, right? So this weight is equal to the buoyant force. Okay, so FB. Okay, so that's the idea behind this buoyancy phenomenon. Okay, so now let's try um, to illustrate. Let's say if we have this free surface and then we have this, let's say, the bottom surface, and let's say this is a fluid or water. Now, if this is our solid body and our solid body has a weight and that weight acts at the centroid. Okay, and we have learned already that the buoyant force is equal to the weight of the fluid, uh, of the I mean the weight of the displaced volume. Okay, so let's say we have F sub B right here, but of course this one should act also at the centroid. So this center, the centroid where the buoyant force is acting can be either concentric to this or can be also different depending upon the shape, of course. Okay, so um, if if the buoyant force is greater than the weight, so it means that there's much force acting upward compared to the force that's acting downward, then of course we will have a condition that's what we call a floating condition. Okay, so this is our floating condition. Now, what if our F sub B, our buoyant force, is just equal to the weight? So if that's the case, then we'll have a drawing something like this. So this is our weight, then this is our buoyant force, and if they're just equal, then we'll have a condition that's called a suspended condition. And if we have a buoyant force that's greater than the weight, then of course we'll have a sinking condition. Okay, so again, if the buoyant force is greater than the weight, then of course that object will float, and if they're just equal, then somewhere it will be suspended somewhere right here. And then if the buoyant force, oh sorry, the buoyant force is less than less than the weight, then it will sink. Okay, so this one is what we call as submerged condition. Then this one is the floating condition. We can also look at this scenario in terms of the density. So if the density of the solid or this object, if the density of this object is less than the density of the fluid, then that's going to be the floating condition. And if they're just equal, then this will be the condition, a suspended condition. And if the density is way larger than the density of the fluid, then of course it's going to sink. Okay, so this principle of buoyancy actually applied to the design of ships, ship design, or the air balloon designs, and similar applications, the floaters and things like that. Okay, so now I guess we'll have to do a sample problem regarding this. And the first problem is this one. Okay, so for the first problem, um, a zero point 0.5 meter cube of a solid timber floats in water as shown in the figure. Find the submerged depth of the cube knowing that the density of timber is 0.6 tons per meter cube. Okay, so we have a solid object right here that has a dimension of zero point 0.5 by zero point 0.5 by zero point 0.5. Okay, so if we draw the solid, it will look something like this. So this is 0 0.5, 0 0.5, and the depth is also 0 0.5. And the problem gives us the density of the timber. And the density of the timber is 0.6 tons per meter cube. Now, this tons is in terms of the mass. Okay, so that's actually equal to 1,000 kg, right, per ton. Okay, so we can actually solve for the unit weight of this. We can convert this mass density into the specific weight. Okay, so since we have the volume, we can determine actually the displaced volume as well. Um, Plus we have the weight also, the weight, I mean the total weight of this solid object. Then it, we can later on find for this depth. Okay, so for the solution, okay, so the first step is to draw the free body diagram. Since it's all about the force analysis, then I think this one will help us also visualize what's going on, or what's going on in this system. Okay, so to draw the free body diagram, then let's say this is our timber, and we have a weight, right? And we also have a um, a buoyant force, right? So this is our FB, this is our weight. Okay, and our weight, the equation for the weight is just simply the unit weight times, right? The unit weight times the volume of the solid. And this one, the equation for this is the unit weight of the fluid times the displaced volume. Okay, so since we have the mass density, then we can actually solve for the unit weight of the timber. Okay, so the unit weight is equal to the mass density times the gravitational acceleration. We have here 0.6 tons per meter cube, and that tons is equal to 1000 kg per ton times the 9.81 meters per second squared. Okay, and the value of this is 5.886 kilonewtons per meter cube. Okay, so now we can solve for the weight. Right? Solve for the weight of the timber. Okay, so weight is just simply the unit weight times the volume, and this one is 5,886 newton per meter cube, and the volume, this is the volume of the cube, which is 0 0.5 times 0 0.5 times 0 0.5. So it's just 0 0.5 raised to 3, and our value here is 735.75 newtons. Okay, so now we have the weight, and we know that the that the summation of forces along the y direction is that the weight is just equal to this buoyant force. Okay, so let's write here, applying now the equilibrium condition. Okay, so summation of forces along the y is equal to 0. Okay, so let's say the upward is positive, then we have that the buoyant force is equal to the weight, and therefore, but since our right, but since FB is equal to the weight of the fluid times um, the displaced volume, then therefore, we can write that our V sub D, our displaced volume, is just simply, right, they're just the same. So this will be our weight divided by the unit weight of the fluid. Okay, so what is our weight? That's 735.75 newtons divided by the specific weight of, right, of water, which is 9,810 kilograms per, oh sorry, this is newton per meter cube. Okay, so our value for the displaced volume is 0.075 meter cube. Okay, so since we have the volume, we have the volume, we can compute for the depth. Okay, so since we had the volume, and if we try to project this, okay, so this is something like this, and this is our portion of the submerged volume. So the portion of submerged volume is this one. Therefore, this is 0.5, this is also 0.5, and what's left is the height. So therefore, if you write here, V sub D is just equal to the area, right? That's the area underneath. So that's the area. Area times what? Times the depth. Okay, so since we have this and we have the value for our area, then we can solve for the depth. So depth is just simply the displaced volume divided by area, which is 0.075 meter cube divided by 0.5 by 0.5. That's in meters squared, and therefore our depth is 0.3 meters. Okay, so that's the answer for this problem. Okay, so just to do a recap, we have this problem that's floating, and we're given the volume as well as um, the 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 unit weight, the unit weight of this solid. Okay, so what we did first is to draw the free body diagram so that we can visualize which one is missing, or which one are we going to solve directly or something. Then after that, we found out that the weight is just equal to the unit weight times the volume, and we have this value. We can solve for this value. And for this one, what we don't have here, the unknown, is the V sub D. Okay, so what we did first is to solve for the weight, because once we have the weight, then we can apply the equilibrium equations. Summation of forces y equal to 0, and the buoyant force is just simply equal to the weight, right? In terms of this equilibrium condition. Okay, and once we solve this, then we can actually apply the equation and solve for this unknown v sub d. Okay, so v sub d is therefore 0.075. Okay, so that's our displaced volume, and we are asked to find for the depth. So the displaced volume um, divided by the area. Okay, and the area is just simply zero point 0.5 by zero point 0.5. Okay, so what we get is 0.3 meters. Okay, so in the next video, we'll be doing some more problems regarding this buoyancy.